What if the very thing once blamed for holding back our technology could actually unlock a brighter, more efficient future? That's exactly what new research from Dr. Dong-Soo Han's team at the Korea Institute of Science and Technology, KIST, is revealing about the phenomenon of spin loss in spintronics, a field many are calling the biggest leap forward in next-generation electronics. But here's where it gets controversial. Instead of fighting against spin loss, KIST's team is embracing it as a secret weapon to drive ultra-low power consumption in cutting-edge devices. Let's start with the basics. Spintronics is an exciting area of research that uses not just the charge of electrons, like traditional electronics, but their quantum property called spin. By controlling the direction of this spin, researchers can represent digital information in ways that promise much faster speeds, dramatically lower energy usage, and data storage that isn't erased when power is cut, a quality known as non-volatility. Imagine your computer booting up instantly, and your phone battery lasting many times longer. Spintronic memory devices and processors use magnetic materials that swap between different states by changing the direction of their internal magnetization, effectively storing the binary zeros and ones that make digital computing possible. Here's the problem, or so everyone thought. When you send an electric current through a magnetic material to switch its state, some of the vital spins are lost before they reach their destination, a phenomenon known as spin loss. Historically, engineers saw this as wasteful, a loss of the very resource needed to trigger those state changes. As a result, workarounds to minimize spin loss and boost precision became a main focus. But KIST's recent findings flipped this script entirely. Through meticulous experiments, Dr. Han's team discovered that spin loss isn't just a leaky faucet to be fixed. Instead, as these spins drizzed out from the magnetic layer, they trigger a subtle yet powerful reaction that actually helps the material switch its magnetization direction more quickly and with much less external energy. It's a bit like discovering that excess heat escaping from your car engine could actually charge your battery instead of just wasting energy. Here's the part most people miss. By cleverly using spin loss, the researchers managed to triple the energy efficiency of magnetization switching compared to standard processes. In today's world of energy-hungry computing, especially as artificial intelligence, AI workloads, and data-heavy edge computing become more common, this breakthrough could mean smarter devices with much longer battery life and a smaller carbon footprint. What's more, this technique doesn't require exotic new materials or complex redesigns of existing chips. It's designed to slot in smoothly with the manufacturing technologies already used in semiconductor fabs worldwide. That means the transition from lab experiment to real-world, or is it a durable, foundational shift that will reshape memory and processing for everything from AI model training to ultra-responsive neuromorphic chips, the analog-inspired processors modeled after the brain. The potential splash zone here is enormous. The team's technique could help AI chips and memory modules operate at the edge, right on your phone or in industrial sensors, without the need for bulky batteries or cooling. Imagine running advanced facial recognition on a tiny device with almost no power draw, or training smart assistants that never need to connect to the cloud. Dr. Han has made it clear. While the world races to perfect AI hardware, the old goal of simply reducing spin loss is no longer enough. By turning perceived drawbacks into assets, KIST's researchers suggest a future where technology evolves not just through new materials, but smarter use of physical phenomena once seen as problems to be solved. Unsurprisingly, this work, published in Nature Communications and supported by leading science agencies in South Korea, has sparked intense interest in the global scientific community. Will this creative approach to spintronics send ripples through how we design computers and manage the world's energy demands? In closing, the KIST findings invite us all to reconsider what we think of as waste or loss in science and technology. Is it time we rethink more of the so-called inefficiencies that shape entire industries? With the future of electronics, AI, and even the sustainability of cloud computing at stake, where do you stand? Do you believe transforming spin loss into an energy asset is the path forward, or are there hidden downsides waiting to be uncovered? Sound off with your thoughts and let's debate. Sometimes yesterday's waste turns out to be tomorrow's wonder.